Physics, at its heart, seeks to uncover the fundamental laws governing the universe. These laws are the bedrock upon which our understanding of reality is built. They guide us in deciphering the mysteries of existence, from the tiniest particles that make up matter to the vast expanses of space that stretch beyond our imagination. We yearn for a single, elegant framework that can explain the behavior of everything, from the smallest particles to the grandest galaxies. This desire for simplicity and coherence drives us to seek a theory that can unify the forces of nature, a theory that can bridge the gap between the quantum world and the cosmos. This quest for a unified theory has captivated physicists for centuries, driving us to seek connections between seemingly disparate phenomena. From the early musings of ancient philosophers to the groundbreaking work of modern scientists, the journey has been long and arduous, yet each step brings us closer to a deeper understanding of the universe. Could there be one overarching principle, one master rule that governs it all? A principle so fundamental that it underlies every aspect of reality, weaving together the fabric of the cosmos in a seamless tapestry? A rule so profound that it could simplify our understanding of the cosmos and reveal the hidden connections between all things? Such a principle would not only revolutionize physics, but also transform our perception of the world and our place within it. This essay explores the intriguing possibility that such a principle exists, a principle rooted in the idea of optimization and efficiency. By examining the patterns and regularities in nature, we may uncover the key to a unified theory, a theory that elegantly explains the complexity of the universe with simplicity and grace. Imagine a simple scenario. 2 points connected by a sloping path. What is the fastest way for an object to travel between these points under the influence of gravity? This seemingly straightforward question, known as the brachistochrone problem, has intrigued mathematicians and physicists for centuries. At first glance, one might assume the shortest path, a straight line, would be the fastest. However, the brachistochrone problem reveals the subtle interplay between distance, speed, and acceleration. The fastest path is not the shortest, but rather a curved path called a cycloid.
Using my newly developed calculus, I demonstrated that the cycloid indeed represented the path of least time. This was a triumph of geometry and mathematical rigor. The cycloid's unique shape allows an object to accelerate rapidly at the beginning of its descent, gaining enough speed to compensate for the longer path it must travel compared to a straight line.
Sir Isaac Newton, a giant of physics and mathematics, tackled the brachistochrone problem in the 17th century. Newton's solution was a triumph of geometry and mathematical rigor.
I drew inspiration from an intriguing principle in optics proposed by Pierre de Fermat, known as Fermat's principle of least time. Fermat's principle is a cornerstone in the field of optics, and it fundamentally changed our understanding of how light behaves. According to this principle, when light travels from one point to another, it always chooses the path that takes the least amount of time. This might seem counterintuitive at first, but it beautifully explains phenomena such as the bending of light when it passes through different mediums like air and water. Fermat's insight was revolutionary because it provided a simple yet profound explanation for complex optical behaviors. This principle states that light always travels between 2 points along the path that takes the least time. Imagine a bird flying directly between 2 trees, or a river taking the shortest route through a landscape. These are natural examples of the principle of least time in action. The idea is that nature is inherently efficient, always seeking the most optimal path. I realized that the brachistochrone problem could be elegantly solved by applying a similar principle to mechanics. The brachistochrone problem, which asks for the shape of the curve down which a bead will slide from one point to another in the least time, can be approached using the same logic. By considering the path of least time, we can determine the optimal curve, which turns out to be a cycloid.
Shortly after Newton's solution, Swiss mathematician Johann Bernoulli approached the problem from a different angle. Bernoulli was fascinated by the idea that nature might have an inherent preference for efficiency. He saw the brachistochrone problem as a perfect opportunity to explore this concept further. Bernoulli proposed that nature, in a sense, chooses the path of least time for objects moving under the influence of gravity. This was a groundbreaking idea, because it suggested a deep connection between the principles governing light and those governing mechanical motion. By applying Fermat's principle to mechanics, Bernoulli was able to derive the same cycloidal curve as the solution to the brachistochrone problem. This insight paved the way for a deeper understanding of the connection between mechanics and optics. It showed that the same fundamental principles could be applied across different fields of science, leading to a more unified view of the natural world. The principle of least time is not just a fascinating concept in optics. It is a powerful tool that can be used to solve a wide range of problems in physics and beyond. Section 5. Fermat's principle guiding light's path.
Fermat's principle of least time had revolutionized optics, explaining why light bends when it passes from one medium to another, a phenomenon known as refraction.
Snell's law, which quantifies refraction, can be derived directly from Fermat's principle.
The principle states that light sniffs out all possible paths and chooses the path that minimizes travel time.
This simple yet powerful idea elegantly explains the behavior of light, suggesting a deeper principle at play.
Inspired by the work of Fermat and Bernoulli, I sought to generalize the principle of least time to a broader context.
He introduced the concept of action, a quantity that combines energy and time, as a fundamental measure in physics.
I proposed that nature doesn't just minimize time, but rather minimizes action.
This principle, known as the principle of least action, states that the path taken by a particle between 2 points is the one that minimizes the action associated with that path. The principle of least action suggests that nature operates with a kind of economy, always seeking the most efficient way to achieve a particular outcome. Whether it's light traveling through different media or a ball rolling down a hill, nature seems to optimize its actions, minimizing the expenditure of this mysterious quantity we call action. This principle has profound implications for our understanding of the universe. It suggests that the laws of physics are not arbitrary, but rather reflect a deep-seated tendency towards efficiency and optimization. The principle of least action has proven to be a powerful tool in physics, forming the bedrock of classical mechanics and playing a crucial role in the development of quantum mechanics and even general relativity. It provides a unifying framework for understanding the behavior of both particles and fields. The dream of a unified theory, a single framework that encompasses all of physics, hinges on finding principles that transcend the specific details of individual phenomena. The principle of least action, with its ability to describe everything from the motion of planets to the behavior of subatomic particles, offers a tantalizing glimpse of such a unifying principle. The quest to uncover the fundamental laws of the universe is a testament to our innate curiosity and our desire to find order in the apparent chaos of the cosmos. From the earliest civilizations, humans have looked up at the stars, wondering about the forces that govern their movements. This relentless pursuit of knowledge has driven countless discoveries, each one peeling back another layer of the cosmic mystery. The principle of least action, with its elegance and its ability to connect seemingly disparate areas of physics, represents a significant step towards this ultimate goal. This principle, which states that the path taken by a system between two states is the one for which the action is least, is not just a mathematical abstraction. It is a profound insight into the workings of nature, revealing a hidden simplicity in the complex dance of particles and forces. While the search for a complete and unified theory continues, the principle of least action stands as a beacon of hope, suggesting that the universe might indeed be governed by principles of profound simplicity and elegance. This principle has found applications in various fields, from the motion of planets to the behavior of light, and even in the quantum realm where particles seem to defy our classical intuitions, suggesting that the universe might indeed be governed by principles of profound simplicity and elegance. It is a reminder that the beauty of nature often lies in its simplicity. The principle of least action is a testament to this, showing us that the most complex phenomena can often be understood through simple, elegant laws. It reminds us that the most fundamental laws of nature often reveal themselves not in complexity, but in the elegant dance of optimization and efficiency. This principle is a guiding light for physicists, offering a glimpse into the underlying order of the universe. It is a call to continue exploring, to keep seeking the elegant truths that lie hidden in the fabric of reality, but in the elegant dance of optimization and efficiency. As we continue to explore the cosmos and delve deeper into the mysteries of the universe, the principle of least action will remain a cornerstone of our understanding, guiding us towards a deeper appreciation of the elegance that underpins the natural world.